13 billion years ago, the universe should have been young and unfinished, yet the ancient galaxy that broke every cosmology model appears already massive, organized, and mature. Its stars formed far too quickly, its structure emerged far too early, and every observation insists it should not exist. Astronomers didn't find a mistake in the data, they found a problem in the models. This is the galaxy that forced cosmology to confront the possibility that the early universe evolved much faster than we ever thought possible. Broken models. From the deepest reaches of space, ancient light arrives without announcement, and in its soft persistence, it leaves behind broken models, carefully constructed frameworks that once described the universe with confidence, now strained by what that light has chosen to reveal. For decades, cosmology rested on a remarkably successful structure known as the lambda-cold dark matter model. It describes a universe born hot and dense, expanding smoothly, with structure forming slowly as invisible dark matter gathered ordinary gas into growing halos. Galaxies, in this view, were patient achievements, assembling piece by piece over billions of years. By the time the universe was a few 100 million years old, complexity was expected to be tentative and incomplete. When NASA's James Webb Space Telescope began observing the distant universe in 2022, it was built to refine this picture, not overturn it. Its infrared instruments were designed to see through cosmic expansion, capturing light stretched by time itself. What Webb uncovered in its deepest surveys, Sears, Jades and others, was not chaos but confidence. Galaxies appeared unexpectedly bright and compact, already rich with stars at a time when the universe should barely have been capable of such productivity. These were not subtle deviations. Some early galaxies displayed stellar masses rivaling those of modern systems, emerging less than 500 million years after the Big Bang. Under standard assumptions, there simply should not have been enough time. Gas must cool, collapse, ignite into stars, and survive the violent feedback those stars unleash. Supernovae and radiation are meant to slow growth, not accelerate it, yet the observed galaxies seem to have formed efficiently, rapidly, and repeatedly. The tension does not arise from a single observation, but from consistency. Independent analyses, using different datasets and methods, repeatedly pointed to the same conclusion. Early galaxies were forming stars at rates that strain existing simulations. Their brightness suggested dense populations of stars. Their structure suggested organization, not infancy. Their very existence pressed against the temporal boundaries imposed by cosmological theory. Importantly, this does not imply that cosmology is fundamentally wrong. Lambda CDM still predicts the cosmic microwave background with extraordinary precision. It still explains large-scale structure and gravitational lensing across billions of light-years. But models are only as strong as their assumptions, and here those assumptions begin to show stress. Star formation efficiency, the behavior of dark matter on small scales, and the role of feedback in the early universe all become uncertain under this new light. One uncomfortable detail lies in how mature these galaxies appear. Their light shows hints of multiple generations of stars, implying earlier rounds of formation that must have occurred even closer to the universe's beginning. Heavy elements, carbon, oxygen, and other products of stellar fusion are detected sooner than expected. These elements require stars to live and die before they can exist in abundance. Their presence suggests a universe that wasted little time. Cosmology has encountered such moments before. In the 1960s, quasars appeared impossibly energetic. In the late 1990s, the discovery of cosmic acceleration forced the introduction of dark energy. Each time, models adjusted rather than collapsed. The universe did not apologize for its behavior. It simply continued, indifferent to human expectation. What makes this moment distinct is its quiet nature. There is no dramatic explosion, no singular anomaly. Instead, there is a steady accumulation of evidence that the early universe may have assembled structure faster than our timelines comfortably allow. Broken models do not announce themselves loudly. They emerge gently, through data that refuses to align neatly with prediction. As cosmologists refine simulations and revisit assumptions, one thing becomes clear: the early universe was not merely a slow prelude to complexity. It may have been an era of rapid construction, where matter organized itself with surprising efficiency. The models are bending, not failing, reshaping themselves around a reality that appears less patient than once believed. In the glow of these distant galaxies, another implication begins to surface. If such structures existed so early, then their internal clocks written into their stars may be telling a deeper story about age itself and about how quickly the universe learned to build. Unexpected age. Long before the universe was expected to look settled or mature, its light already carries the signature of unexpected age, an ancient calm embedded in galaxies that should, by every prior account, still have been learning how to exist. Age in cosmology is not measured the way it is in human experience. No calendar marks the passage of time across billions of years. Instead, astronomers read age indirectly through distance, redshift, and the subtle fingerprints embedded in starlight. As the universe expands, light stretches with it, shifting toward redder wavelengths. The farther that light has travelled, the earlier in cosmic history it was released. Using this principle, the James Webb Space Telescope has identified galaxies at redshifts greater than 10, meaning their light left them when the universe was less than 500 million years old. Within that narrow window, theory expected fragility. Early galaxies were meant to be small, irregular, and inefficient collections of gas only beginning to collapse under gravity. What Webb revealed instead was far more composed. Spectral data showed galaxies that were not merely present, but established. Their brightness implied large populations of stars. Their shapes suggested structure. In some cases, their light indicated stellar populations that appeared already hundreds of millions of years old. This is where the discomfort begins. Stars are not born fully formed. Gas must cool, fragment, and ignite. Massive stars live briefly and die violently, enriching their surroundings with heavier elements. Only after several cycles can a galaxy develop chemical complexity. Yet Webb's observations revealed signatures of carbon and oxygen elements that require prior generations of stars appearing far earlier than anticipated. Early analyses initially produced age and mass estimates so extreme that they bordered on impossible. Subsequent work refined those numbers, accounting for dust, stellar evolution, uncertainties, and improved modelling. Even after revision, many galaxies remain older and more massive than standard timelines predict. The problem has not vanished. It has simply become more precise. To reconcile this, astronomers have explored the idea that star formation in the early universe may have been extraordinarily efficient. Gas clouds could have collapsed rapidly, converting matter into stars with minimal delay. Feedback processes, stellar winds, and radiation that normally slow growth may have behaved differently in denser early environments. None of these ideas violate known physics, but together they suggest that cosmic youth was far more productive than previously assumed. Importantly, this does not challenge the measured age of the universe itself. Independent observations from the cosmic microwave background to the expansion rate of space continue to converge on an age of approximately 13.8 billion years. The tension lies not in when the universe began, but in how quickly complexity emerged afterward. There is a subtle shift in perspective here. For much of modern cosmology, complexity was treated as a late arrival, emerging gradually as the universe cooled and expanded. Webb's observations hint at a different rhythm. The early universe may have been a period of accelerated organization, with galaxies assembling rapidly before settling into slower evolutionary paths. Unexpected age, then, is not merely a numerical discrepancy. It is a narrative adjustment. These galaxies are telling us that cosmic time does not unfold at a single, steady pace. Some eras move swiftly, compressing generations of structure into remarkably short spans. As this understanding settles, attention turns naturally from age to the mechanisms that could make such rapid growth possible. The question is no longer whether these galaxies are old for their time, but what unseen influences allowed them to mature so quickly, shaping the universe long before its story was thought to have properly begun. Too massive. Light from galaxies born when the universe was still trembling in its cradle arrives bearing an unsettling truth. They are too massive. When the James Webb Space Telescope, JWST, turned its golden mirror toward the farthest observable reaches in 2022, it did not find the delicate, fragmented proto-galaxies astronomers anticipated. Instead, gleaming within JWST's infrared gaze were fully formed galaxies, luminous, dense, and astonishingly heavy, existing a mere 450 million years after the Big Bang. According to every cosmological model built over the last 50 years, Such objects simply should not exist so early. The universe at that age was supposed to be a thin fog of hydrogen and helium, its matter only just beginning to clump under gravity's gentle tug. Yet here were galaxies boasting stellar masses exceeding 5 billion suns, comparable to the Milky Way today. Mass in astronomy is no abstract concept. It is measured through a galaxy's luminosity, its spectral colour, and the motion of its stars. JWST's near-infrared camera, NIRCam, captures the aggregate glow of countless stars within these distant systems. When astronomers feed this data into stellar population synthesis models, software that reconstructs a galaxy's history from its light, the results defy prediction. Simulations based on the lambda-cold dark matter LCDM model, the bedrock of modern cosmology, show that at redshift times z is greater than 10 the window JWST probes, typical galaxies should weigh less than 1 billion solar masses. The observed galaxies are 5 times heavier. Why does this rupture our understanding? Galaxy formation is a slow dance. First, invisible dark matter halos must coalesce. Only then can ordinary gas fall inward, cool, fragment, and ignite stars. Feedback processes radiation from hot young stars and explosive supernovae, then blow gas back out, slowing time's further growth. In the early universe, this feedback was assumed to be especially potent, yet these galaxies appear untouched by it. Their star formation rates are ferocious, converting gas into stars at speeds 10 times faster than in the Milky Way today. To achieve such mass so quickly, gas must have collapsed with near-perfect efficiency, a scenario our physics struggles to explain. Some researchers propose a solution hiding in the dark. Perhaps early dark matter halos formed earlier, denser, and more concentrated than LCDM predicts. Others suggest the initial mass function, the distribution of stellar masses at birth, was top-heavy, flooding the young universe with massive, short-lived stars that burn bright and die fast, artificially inflating luminosity measurements. But even after applying these adjustments, the discrepancy remains. The galaxies are still too massive. This excess mass whispers of deeper unknowns. If galaxies assembled this rapidly, the timeline for cosmic reionization, the epoch when the universe's neutral hydrogen fog was burned away by starlight, must be revised. Brighter, earlier galaxies could have completed reionization times hundreds of millions of years sooner times than previously thought. There is a quiet humility in this discovery. For decades, cosmology painted the infant universe as simple, orderly, and patient. JWST reveals a cosmos that built cathedrals before laying foundations. These galaxies, too massive for their youth, remind us that the universe operates on its own schedule, lavish, swift, and utterly indifferent to human expectation. As their ancient light washes over our detectors, it carries more than mass. It carries a challenge etched in starlight. And within that challenge lies the next clue, a signal older than the galaxies themselves, waiting to be read. Ancient signals. Photons forged in the first stellar nurseries have crossed 13 billion years of expanding space. Their ancient signals, stretched thin yet stubbornly persistent, finally registering on our instruments as faint, red-shifted whispers from the dawn of time. When JWST observes a galaxy at redshift times z equals 12, it captures light emitted when the universe was only 380 million years old. That light began its journey as brilliant ultraviolet radiation from hot, young stars. As space itself expanded, each photon's wavelength elongated a process called time's cosmological redshift, time's shifting ultraviolet light into the infrared. JWST's instruments, cooled to near absolute zero, are uniquely sensitive to this infrared glow. The signal is not a radio burst or a mysterious pulse. It is starlight, preserved across eons. Decoding these signals begins with spectroscopy. JWST's near-infrared spectrograph, NIRSpec, splits the incoming light into its component colours, producing a spectrum, a barcode of dark absorption lines and bright emission lines. Each line corresponds to a chemical element. In 2023, NIRSpec analysed spectrum after spectrum from times Z is greater than 10 galaxies and found something extraordinary. Bright blue oxygen lines. Oxygen cannot exist in a pristine universe. It is forged exclusively in the cores of massive stars, which must live, explode as supernovae, and scatter their enriched material into space, a process requiring millions of years. Yet here was oxygen in galaxies that, by cosmic reckoning, were barely 300 million years old. The signal screamed of prior stellar generations that time should not have had time to form. Age is read from the spectrum too. The strength of the Balmer break, a sharp dip in light at specific infrared wavelengths, reveals how long a galaxy's stars have been shining. A strong Balmer break indicates older stellar populations. In several early galaxies, the break appeared two strong times for their redshift-derived age, suggesting stars within them were older than the universe permitted at that epoch. This tension birthed the unexpected age paradox, a paradox written directly into the ancient signals themselves. Dust complicates the story. Interstellar dust absorbs blue light and re-emits it as infrared glow, reddening a galaxy's spectrum and mimicking an older stellar population. Early analyses of JWST data overestimated masses and ages because they underestimated dust. Refined models now account for dust grain size, composition, and distribution. Even after correction, however, many galaxies retain spectral signatures of chemical maturity, far earlier than theory allows. Carbon, neon, and iron, all products of stellar alchemy, appear alongside oxygen. These signals are more than data. They are time capsules. Each photon travelled through the evolving universe, past quasars, through galaxy clusters, surviving cosmic expansion to reach us unchanged. To detect such a signal is to hold a fragment of creation a direct line to the universe's first luminous moments. In their quiet persistence, these ancient signals dissolve the barrier between past and present. They remind us that observation is a form of time travel, and as we learn to listen more keenly, the cosmos continues to transmit its earliest, most profound messages we are only now beginning to understand. Within these spectral fingerprints lies the imprint of gravity's first triumphs. Now we follow gravity's hidden role in shaping the impossible. Redshift mystery. Redshift mystery begins not with what we can see, but with what happens to light during its journey through an expanding universe. A journey that stretches wavelengths, distorts colours, and occasionally produces measurements that refuse to align with the elegant equations meant to predict them. When Edwin Hubble first observed galaxies receding in 1929, he noticed something peculiar. Their light was shifted toward the red end of the spectrum, and the farther away a galaxy sat, the more pronounced that shift became. This redshift became cosmology's most reliable ruler, a method for converting wavelength into distance and distance into time. The principle seems straightforward. As space expands, photons stretch with it, their wavelengths lengthening proportionally to how much the universe has grown since they were emitted. Measure the redshift, and you measure cosmic history itself. For decades, this relationship held beautifully. Galaxies at redshift 1 appeared as they were roughly 8 billion years ago. Those at redshift 6 revealed the universe at less than 1 billion years old. Cosmologists built entire frameworks around this correspondence, confident that redshift was not merely a proxy for distance, but a direct window into the past. Then the James Webb Space Telescope began returning data from galaxies at redshifts exceeding 10, and something unexpected emerged. Not contradictions exactly, but subtle tensions, galaxies appearing brighter than anticipated, more structured than models predicted, their redshift values occasionally requiring adjustments that pushed against comfortable assumptions. Some early candidates displayed redshifts initially measured near 16 or 17, which would place them extraordinarily close to the Big Bang. Subsequent spectroscopy revised several of those estimates downward, but the frequency of such revisions raised questions about how reliably redshift translates to cosmic age in the universe's earliest moments. The mystery deepens when considering that redshift depends on more than just expansion. Gravitational fields also redshift light, as do the motions of galaxies through space. Disentangling these effects requires precise measurements and careful modelling. For distant galaxies, where light has travelled for over 13 billion years, even small uncertainties compound significantly. There is also the matter of the Hubble tension, an unresolved discrepancy between two methods of measuring cosmic expansion. Observations of the early universe, derived from the cosmic microwave background, suggest one expansion rate. Measurements of nearby supernovae and galaxies imply another, faster rate. The difference is modest, roughly 9%, but persistent across independent studies. If the expansion rate has varied in unexpected ways, then the relationship between redshift and time may not be as straightforward as once believed. Webb's observations have not overturned the redshift framework, but they have illuminated its edges. In the universe's infancy, conditions were dense, turbulent, and still settling. Dust obscures light. Intense radiation from young stars alters spectra. Gravitational lensing magnifies and distorts. Each of these factors introduces complexity into what should be a clean measurement. Redshift remains cosmology's most powerful tool, yet it carries embedded assumptions about how the universe expands, how matter behaves, and how light propagates through intergalactic space. Webb's galaxies have gently tested those assumptions, revealing places where the tool works brilliantly and places where it strains. The mystery is not that redshift fails, but that it succeeds almost everywhere except in the narrow critical windows where the universe was still learning its own rules. In those moments, measurements shimmer with ambiguity, and the elegant correspondence between colour and time becomes something more intricate. Light itself, stretched across billions of years, carries within it not just information, but uncertainty, a reminder that what we perceive as distance may sometimes be entangled with forces and histories far stranger than simple expansion can explain. Time illusion. Time illusion is woven into the very fabric of cosmology, not as error or misperception, but as an unavoidable consequence of observing a universe where time itself bends, stretches, and flows at rates determined by gravity, velocity, and the relentless expansion of space. When we observe a distant galaxy, we do not see it as it is, but as it was sometimes billions of years in the past. This is not metaphorical. The light reaching our instruments today left that galaxy when the universe was younger, denser, and governed by different physical conditions. In this sense, telescopes are not merely instruments of distance, but of time, allowing us to peer backward through cosmic history. Yet this relationship between observation and time conceals something more unsettling. Time does not pass uniformly across the universe. Einstein's general relativity established that time runs differently depending on gravitational fields and relative motion. Near massive objects, time slows. For objects moving at high velocities, time dilates. The universe itself, expanding and evolving, creates a context where the very meaning of when becomes ambiguous. Consider what this means for early galaxies observed by Webb. When we say a galaxy existed 500 million years after the Big Bang, we are speaking from our reference frame, here and now. But from the perspective of that galaxy, if such a perspective could meaningfully exist, time flowed differently. The intense gravitational fields of the early universe, the higher density of matter, and the rapid expansion rates all influenced how clocks would have ticked in that environment. This creates a peculiar form of illusion. We assign ages to galaxies based on redshift and expansion models, but those ages are calculated using our understanding of time's passage. If the early universe experienced time differently, if processes unfolded at rates we cannot directly measure, then the ages we assign may be approximations rather than absolutes. Cosmologists account for this through proper time and moving coordinates, mathematical frameworks designed to reconcile these differences. Proper time measures the experience of time for an observer moving with the expansion. Co-moving coordinates remove expansion effects, creating a static map of cosmic structure. Both are necessary, yet both are abstractions, models layered over a reality that resists simple description. The illusion deepens when considering gravitational time dilation in the early universe. Regions of higher density proto-galaxies collapsing under their own gravity would have experienced time more slowly relative to the surrounding space. Stars forming in these regions aged according to their local clocks, which did not necessarily align with the cosmic clock ticking in less dense regions. This is not merely theoretical. Observations of gravitational lensing, where light bends around massive objects, reveal time delays between multiple images of the same distant event. The light paths differ in length and gravitational depth, arriving at Earth separated by days or even years despite originating simultaneously. Time, in this context, is not a single flowing river, but a landscape of varying rates. For early galaxies observed by Webb, the illusion manifests as uncertainty. When we estimate that a galaxy is 300 million years old based on its stellar population, we rely on models of stellar evolution calibrated to local conditions. But if time flowed differently in that galaxy's environment, those models may require adjustment. The stars might be younger or older than their spectra suggest. Time illusion does not invalidate cosmology, but it complicates the narrative we construct from distant light. The universe is not a film playing backward. It is a tapestry where every thread experiences duration at its own pace, shaped by mass, motion, and the curvature of space itself. What we perceive as cosmic history is, in truth, a synthesis, our attempt to reconcile countless local timelines into a single coherent story, knowing that each timeline bends slightly away from the others in ways both subtle and profound. Deep time. 13.8 billion years is not merely a number, it represents deep time, a span so vast that human comprehension falters before it, leaving us to trace its passage, not through lived experience, but through the faint echoes preserved in light and matter across an unfathomable distance. The concept of deep time entered human thought relatively recently. In the 18th century, the Scottish geologist James Hutton examined rock formations and realized that Earth's history stretched far beyond biblical chronology. He saw layers of sediment, ancient seabeds lifted into mountains, and volcanic intrusions cutting through stone, all requiring durations that exceeded comfortable imagination. Hutton called this "no vestige of a beginning, no prospect of an end," a statement that unsettled his contemporaries but opened geology to timescales measured in millions of years. Cosmology extended that vision further still. When Edwin Hubble demonstrated in 1929 that the universe was expanding, the implication became unavoidable. If everything is moving apart now, then everything must have been closer together in the past. Trace that motion backward far enough, and you arrive at a point where space, time, and matter emerged together roughly 13.8 billion years ago. Deep time in cosmology operates differently than it does in geology. On Earth, we can walk across landscapes shaped by ancient processes, touch rocks billions of years old, and hold fossils that once lived. The universe offers no such tactile connection. Instead, deep time reveals itself through redshift, radioactive decay, and the cooling of thermal radiation. The cosmic microwave background light released 380,000 years after the Big Bang reaches us now as faint microwaves, stretched by expansion into wavelengths far longer than visible light. That radiation has been traveling for over 13 billion years, carrying information about conditions when the universe was 1,000 times smaller and 1,000,000 times hotter than today. Comprehending such durations requires recalibration. If the entire history of the universe were compressed into a single year, with the Big Bang occurring at midnight on January 1st, the solar system would not form until early September. Dinosaurs would appear on December 30th. Human civilization would occupy the final minute before midnight on December 31st. Yet even this analogy falls short, because deep time is not merely about duration, it is about change unfolding across scales that defy intuition. Stars are born, burn for billions of years and die, enriching space with heavy elements that become new stars and planets. Galaxies collide over hundreds of millions of years, their shapes warping slowly as gravity orchestrates encounters spanning distances light takes millennia to cross. The galaxies observed by Webb at high redshift exist in our present observations but represent moments from the universe's distant past. When their light began its journey, the universe was young, hot, and structured differently. The photons travelling toward us have moved through expanding space for over 13 billion years, witnesses to cosmic evolution unfolding in a direction we call forward, but which, from our perspective, appears reversed. Deep time does not merely separate us from the early universe, it connects us to it. The hydrogen in our bodies was forged in the Big Bang. The carbon, oxygen, and nitrogen essential to life were synthesized in stars that lived and died before the sun formed. Every atom carries a history measured in billions of years, a lineage extending back through stellar generations to the universe's first moments. Understanding deep time requires accepting that the cosmos operates on scales where human lifetimes are flickers, civilizations are brief, and even stars are temporary. The universe's story unfolds slowly, patiently, indifferent to urgency. Yet within that vast duration, photons have travelled uninterrupted, preserving information from epochs we can observe but never visit, carrying toward us the universe's oldest stories written in wavelengths of light that stretch across distances measured not in kilometers, but in billions of years. First light. The universe spent its earliest moments in darkness, or rather in a state where light existed but could not travel, trapped, scattered, absorbed endlessly by a dense fog of charged particles until, roughly 380,000 years after the beginning, the cosmos cooled just enough for what astronomers call first light to finally break free and stream unimpeded through space, marking the moment when the universe became truly visible for the first time. This event, known as recombination, marked a fundamental transition. Before it, the universe was a hot plasma where electrons moved freely, colliding constantly with photons and preventing light from travelling more than a tiny distance before being scattered again. The entire cosmos glowed, but that glow remained trapped within itself, unable to form clear images or travel far. Then, as expansion cooled the universe to around 3000 Kelvin, roughly the temperature of a red dwarf star's surface electrons combined with protons to form neutral hydrogen atoms. This seemingly simple change had profound consequences. Neutral hydrogen does not scatter light the way free electrons do. Suddenly, photons could move freely. The universe became transparent. The light released at that moment is what we now detect as the cosmic microwave background, or CMB. It represents the oldest electromagnetic radiation we can observe, a snapshot of the universe at 380,000 years old. Since then, that light has been travelling through expanding space, stretched by cosmological redshift from visible wavelengths into microwaves. What began as a warm orange glow now arrives at Earth with a temperature of 2.7 Kelvin, just above absolute zero. The CMB was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, who were calibrating a radio antenna and encountered persistent noise they could not eliminate. That noise turned out to be the echo of the universe's first light, present in every direction, a nearly uniform signal coming from the entire sky. Their discovery confirmed a key prediction of Big Bang cosmology and earned them the Nobel Prize in Physics in 1978. Subsequent missions, COBE in 1989, WMAP in 2001, and Planck in 2009, measured the CMB with increasing precision, revealing tiny temperature fluctuations of only a few millionths of a degree. These fluctuations are not random. They represent density variations in the early universe, regions where matter was slightly more or less concentrated. Those denser regions would eventually collapse under gravity to form the first stars, galaxies, and large-scale structures we observe today. The CMB provides cosmology with its most precise measurements. From its temperature fluctuations, scientists have determined the universe's age, its composition, and its geometry. The data confirms that ordinary matter makes up only about 5% of the universe's total energy content. Dark matter accounts for roughly 27%, and dark energy, the mysterious force driving accelerated expansion, comprises the remaining 68%. First light also reveals something subtly profound. We exist inside a sphere of visibility defined by how far light has travelled since recombination. Beyond that boundary, no information can reach us because no light had yet been released. The CMB represents the earliest possible view, a horizon beyond which the universe remains fundamentally unobservable. That light, now stretched into microwaves, fills the entire cosmos. It passes through us constantly, a relic radiation from when the universe first became transparent. Every square centimetre of sky glows faintly with it, a whisper from 13.8 billion years ago, still travelling, still carrying the imprint of the universe's infancy. First light was not a single event but a transition, occurring over tens of thousands of years as different regions of the universe cooled at slightly different rates, yet the result was the same everywhere. Photons finally escaped and the cosmos opened its eyes. Cosmic dawn. Between the release of the universe's first light and the ignition of its first stars lay a period of profound darkness. Lasting hundreds of millions of years, a cosmic dawn that arrived not suddenly, but gradually, as gravity slowly gathered matter into dense enough concentrations that nuclear fusion could finally begin, transforming the universe from a cold, neutral void into a landscape lit by countless newborn suns. This epoch, occurring roughly between 100 and 400 million years after the Big Bang, marked one of the most dramatic transitions in cosmic history. After recombination released the cosmic microwave background, the universe entered what astronomers call the Dark Ages. No stars existed yet, no galaxies had formed. The cosmos consisted primarily of neutral hydrogen gas, dark matter, and the faint glow of stretched radiation cooling steadily as space expanded. Dark matter played the crucial role during this period, though it remained invisible. Its gravity acted as scaffolding, pulling ordinary matter into increasingly dense clumps. These proto-galactic regions grew slowly, attracting more gas until eventually the pressure and temperature at their cores reached the threshold needed for hydrogen fusion. When that happened, the first stars ignited. These initial stars were unlike anything in the modern universe. Composed almost entirely of hydrogen and helium, the only elements available, they formed without the cooling assistance provided by heavier elements in later generations. Computer simulations suggest they grew exceptionally massive, perhaps 100 to 300 times the mass of our Sun. Such massive stars burn brilliantly but briefly, living only a few million years before exploding as supernovae. The radiation from these population 3 stars, as astronomers call them, began transforming their surroundings. Their ultraviolet light ionized nearby hydrogen atoms, stripping electrons away and creating bubbles of ionized gas that expanded outward. This process, known as reionization, gradually changed the universe's character. Over several hundred million years, these expanding bubbles merged until nearly all the hydrogen between galaxies became ionized once more, completing cosmic dawn. Direct observation of this era remained impossible until recently. The James Webb Space Telescope, launched in 2021, was specifically designed to detect infrared light from this period. Its observations have begun revealing galaxies at redshifts corresponding to 200 to 300 million years after the Big Bang, offering the first glimpses of cosmic dawn itself. What Webb has found challenges expectations. Galaxies appear more numerous and brighter during this period than models predicted. Some show signs of active star formation rates that seem implausibly high for such early times. The efficiency with which these first galaxies converted gas into stars may have exceeded what simulations suggested was possible. Cosmic dawn also left subtle signatures in the cosmic microwave background. The Planck satellite detected slight distortions in CMB polarization that correspond to when reionization occurred, providing independent confirmation that this transformation happened between 400 and 200 million years after the Big Bang, though the exact timeline remains under investigation. The importance of this epoch extends beyond curiosity about beginnings. The first stars synthesized the first heavy elements, carbon, oxygen, iron through fusion, and supernova explosions. These elements mixed into surrounding gas, enriching the raw material for subsequent stellar generations. Without cosmic dawn, the chemistry necessary for planets, life, and eventually observers would never have emerged. The universe's transition from darkness to light was not instantaneous, but unfolded across hundreds of millions of years, a slow awakening that seeded everything that followed. These earliest illuminations were merely preparation, setting the stage for structures that would grow larger, more complex, and stranger than the simplicity of their origins might suggest. Early galaxies. Galaxies in the universe's first billion years were not meant to look established, but early galaxies observed by modern telescopes reveal systems that already possess surprising mass, structure, and organization properties that cosmological models predicted should require far more time to develop. The discovery of these systems represents one of Webb's most significant contributions. Using its near-infrared camera and spectroscopic instruments, the telescope has identified galaxies at redshifts exceeding 10, corresponding to when the universe was less than 500 million years old. Surveys such as JADES, the James Webb Advanced Deep Extragalactic Survey, and SEERS, the Cosmic Evolution Early Release Science Survey, have catalogued dozens of these objects since observations began in 2022. What makes these early galaxies remarkable is not merely their existence but their appearance. Standard cosmological theory describes galaxy formation as a hierarchical process. Small dark matter halos form first, attracting gas that cools and collapses to form stars. These small proto-galaxies then merge over time, gradually building larger systems. The process should be inefficient initially, with early galaxies remaining small, irregular, and faint. Webb's observations show something different. Many early galaxies appear compact and bright, suggesting stellar masses comparable to smaller modern galaxies, despite their youth. Some display structured morphologies, disks, bulges, even hints of spiral features that imply organization emerging far earlier than predicted. One particularly striking example is JADESGS Z130, a galaxy observed at redshift 13.2, placing it roughly 330 million years after the Big Bang. Its spectrum shows clear evidence of oxygen and carbon, elements that require previous generations of stars to produce. The presence of these metals so early implies rapid star formation cycles, with massive stars living, dying, and enriching their environment within the universe's first few 100 million years. Another notable object, Glass Z13, was among the earliest high redshift candidates identified. Initial photometric estimates placed it at redshift 13, though spectroscopic follow-up has refined such measurements. These galaxies consistently demonstrate that structure formation began earlier and proceeded faster than models comfortably allow. The star formation rates inferred from these observations pose additional questions. Converting the observed luminosity into stellar mass requires assumptions about how efficiently gas becomes stars. Even with conservative estimates, many early galaxies appear to be forming stars at rates that challenge theoretical limits. Feedback from supernovae and stellar radiation should slow growth, yet these systems seem to overcome such resistance. There is also the matter of dust. Several early galaxies show signatures suggesting dust is already present, which requires prior stellar generations to produce. Dust forms from elements heavier than helium, carbon, silicon, oxygen ejected by dying stars. Finding dust at 400 million years implies multiple cycles of star formation have already occurred, compressing what should be a gradual process into a remarkably brief period. Cosmologists have proposed several explanations. Perhaps dark matter halos in the early universe collapsed more efficiently than standard models predict. Perhaps the initial mass function, the distribution of stellar masses at birth, favoured more massive stars that lived briefly and enriched their surroundings rapidly. Perhaps gas cooling mechanisms operated differently in the dense early universe. None of these adjustments violate known physics, but together they suggest that the early universe was a more productive environment than previously understood. The galaxies observed by Webb are not anomalies, but representatives of a population that formed quickly, efficiently, and with surprising sophistication. Early galaxies have not overturned cosmology, but they have forced refinement of how structure emerges from initial conditions, reminding us that the universe's youth was perhaps less tentative than its equations once suggested. Star factories. Within the earliest galaxies, something remarkable was happening. Gas was converting into stars at rates so prodigious that astronomers have come to call these systems star factories. Cosmic foundries where matter transforms into light, with an efficiency that modern galaxies can rarely match, producing stellar populations in mere millions of years that should have required billions. The term refers not to a type of galaxy, but to a phase of activity, periods when star formation accelerates to extraordinary levels. In the present-day universe, typical galaxies form stars at modest rates. The Milky Way, for instance, produces roughly 2 solar masses worth of stars per year, a steady but unremarkable pace sustained over billions of years. Star factories operate differently, converting hundreds or even thousands of solar masses of gas into stars annually, blazing through their fuel reserves with remarkable speed. This phenomenon becomes particularly relevant when examining the ancient galaxies detected by Webb. Many show signs of intense star formation activity occurring when the universe was less than 1 billion years old. The brightness of these systems implies massive stellar populations forming rapidly, far faster than hierarchical galaxy formation models predicted. To explain their observed luminosity, these galaxies must have been extraordinarily efficient at turning gas into stars. Star formation efficiency depends on several factors. Gas must cool enough to collapse under its own gravity, but not so violently that feedback from newly formed stars disrupts the process. Supernovae explosions and stellar winds normally blow away surrounding material, slowing further star birth. Radiation pressure from massive stars heats nearby gas, making it harder to collapse. In modern galaxies, these feedback mechanisms limit efficiency to perhaps 1 or 2%. Most gas remains unused or gets expelled. early galaxies appear to have overcome these limitations. Their environments were denser, with more gas concentrated in smaller volumes. The universe itself was denser, meaning gravitational collapse occurred more readily. Gas clouds could fragment into stars before feedback had time to halt the process. Computer simulations suggest that under such conditions, star formation efficiency might reach 10% or higher, explaining how early galaxies built substantial stellar masses so quickly. There is also the matter of initial mass function, the distribution of stellar masses at birth. In modern star-forming regions, most stars are relatively small, with only a few massive ones. But if early star factories preferentially formed more massive stars, each generation would burn brighter and die faster, cycling material back into new stars more rapidly. This would accelerate chemical enrichment and produce the heavy elements observed in early galaxy spectra. Observations support this picture. Webb has detected galaxies with star formation rate densities, the rate per unit area that exceed anything seen locally. Their compact sizes mean star formation occurs in extraordinarily small volumes, concentrating energy and matter in ways that amplify feedback, but also, paradoxically, seem to sustain high formation rates. One example is Goods, ALMA Z701, a galaxy at redshift 7.7, observed forming stars at roughly 300 solar masses per year, despite being less than 1 billion years old. At this rate, it could assemble a stellar mass comparable to a small present-day galaxy in just 100 million years. Star factories in the early universe were not anomalies, but perhaps the norm, representing a phase when conditions favoured rapid growth. These episodes likely ended as gas was exhausted or expelled, after which galaxies settled into slower, steadier evolution. The intensity of these early star-forming episodes raises a natural question about what enabled them, what invisible scaffolding held these galaxies together while they burned so brightly through their reserves. Dark matter. Dark matter announces itself only through its absence, shaping galaxies and clusters through gravitational influence alone, while remaining utterly invisible to every instrument designed to detect light, revealing the universe as something far stranger than the luminous structures we observe, a cosmos where most matter hides in permanent darkness, known only by how it bends space-time and guides the motion of everything we can actually see. The evidence for dark matter emerged gradually through the 20th century. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster and noticed that galaxies within it moved far too quickly for the visible mass to hold them together gravitationally. Either galaxies were about to fly apart, or something unseen was providing additional gravity. Zwicky proposed the existence of Dunkel materie dark matter, though his idea gained little traction at the time. Decades later, Vera Rubin's observations of galactic rotation curves provided stronger evidence. Stars orbiting at the edges of spiral galaxies moved at speeds that should fling them into intergalactic space, if only visible matter provided gravity. Instead, rotation curves remained flat far beyond the visible disk, implying that galaxies are embedded in massive halos of invisible matter, extending well beyond their stars. Further confirmation came from gravitational lensing, where light from distant objects bends around massive foreground structures. The amount of bending indicates total mass, and repeatedly, observations show far more mass than luminous matter can account for. The cosmic microwave background provides additional constraints. Its temperature fluctuations depend on the total matter density in the early universe, and the data require roughly 5 times more matter than can be observed directly. Current estimates suggest dark matter comprises about 27% of the universe's total energy content, compared to just 5% for ordinary matter. The rest is dark energy, an even stranger component driving cosmic acceleration. Dark matter appears to interact only through gravity, passing through ordinary matter without electromagnetic interaction, making direct detection extraordinarily difficult despite decades of experimental efforts. For early galaxy formation, dark matter played an essential role. Its gravity provided the scaffolding around which ordinary matter could accumulate. Because dark matter doesn't interact electromagnetically, it could collapse into dense halos without radiating energy away. These dark matter halos formed first, creating gravitational wells that attracted hydrogen and helium gas. As gas fell into these wells, it collided with itself, radiated energy, and cooled enough to form stars. Without dark matter, structure formation would have occurred far more slowly. Ordinary matter alone would have taken much longer to overcome the smoothing effects of radiation pressure and thermal motion. Dark matter, immune to such influences, could begin clumping immediately after the Big Bang, giving structure formation a head start. The ancient galaxies observed by Webb likely formed within particularly dense dark matter halos that collapsed early. These regions represented peaks in the primordial density field, places where random fluctuations created slightly higher concentrations of dark matter. Gravity amplified these differences over time until they became the halos hosting the first galaxies. Yet dark matter also presents mysteries. Its particle nature remains unknown despite numerous detection experiments. Proposed candidates include weakly interacting massive particles, or WIMPs, and axions, but neither has been confirmed. Alternative theories, such as modified gravity, attempt to explain observations without invoking new particles, though these struggle to match the full range of cosmological data. The ancient galaxies themselves may offer clues. If dark matter behaves unexpectedly on small scales, it could affect how early halos formed and merged, potentially explaining why some galaxies appear more massive or structured than predictions allow. Dark matter remains one of physics' most profound mysteries, a substance comprising most of the universe's mass, yet detectable only through its gravitational fingerprints, silently guiding cosmic evolution while resisting every attempt to grasp its fundamental nature. Gravity rules. Across every scale the universe possesses, from the smallest clumps of dark matter to the largest filaments spanning billions of light-years, one force orchestrates the architecture of everything. Gravity rules not through complexity or subtlety, but through patient, relentless persistence, shaping the cosmos by the simplest possible mechanism. Mass attracts mass, and given enough time, structure emerges from even the tiniest initial differences in density. Isaac Newton formulated the mathematics of gravity in 1687, describing how every object with mass attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This elegant relationship explained planetary orbits, falling apples, and the tides. For 2 centuries, it seemed complete. Then Einstein refined the picture. His General Relativity, published in 1915, revealed that gravity is not a force in the conventional sense, but a consequence of space-time curvature. Mass warps the fabric of space and time around it, and objects follow the curved paths this warping creates. The mathematics became more complex, but the essential behavior remained. Mass attracts mass, governing cosmic structure. In the early universe, gravity's influence began immediately after the Big Bang. Even when the cosmos was a nearly uniform sea of hydrogen, helium, and dark matter, tiny density fluctuations existed regions where matter was microscopically more concentrated. These variations, imprinted during cosmic inflation and visible now in the cosmic microwave background, became the seeds of all future structure. Gravity amplified these seeds through a process called gravitational instability. Denser regions possess slightly stronger gravity, pulling in surrounding matter. This additional matter increased their gravitational pull further, attracting more material in a feedback loop that transformed minuscule density differences into pronounced concentrations over millions of years. Dark matter drove this process during the universe's first few 100 million years. Because it doesn't interact electromagnetically, dark matter could collapse freely, while ordinary matter remained coupled to radiation, prevented from clumping by photon pressure. Dark matter halos formed first, creating gravitational wells deep enough to eventually capture and hold gas once the universe cooled sufficiently for matter and radiation to decouple. The hierarchical structure of the universe today, small galaxies within groups, groups within clusters, clusters connected by filaments, reflects gravity's patient accumulation. Smaller structures formed first, then merged into larger ones through gravitational attraction. Every galaxy cluster observed represents millions or billions of years of gravitational assembly. For the ancient galaxies that trouble cosmological models, gravity played a particularly crucial role. These systems appear to have formed in regions where the primordial density field peaked most sharply. Computer simulations identify such peaks as rare but inevitable statistical fluctuations, places where multiple density waves happen to align, creating exceptional gravitational potential wells. Within these wells, matter fell inward rapidly. Gas clouds collapsed, fragmented, and ignited into stars. The resulting galaxies grew massive quickly because gravity had provided them with particularly deep wells to draw from. The efficiency with which these early systems converted gas into stars may have been enhanced by the stronger gravitational fields in their dense environments. Gravity also holds galaxies together against internal disruptions. Supernovae explosions and stellar winds generate enormous pressures that would blow galaxies apart without sufficient gravitational binding. The fact that early galaxies survived their own violent star formation suggests they resided in substantial dark matter halos, providing the necessary gravitational stability. Observations of gravitational lensing, where foreground mass bends light from background objects, confirm that gravity operates identically across cosmic time. Ancient galaxies lens distant sources just as modern ones do, following the same mathematical relationships Einstein derived a century ago. Gravity does not care about the epoch it operates within or the complexity of the structures it shapes. It simply continues, forever pulling mass toward mass, indifferent to whether it's building the first proto-galaxy or orchestrating the collision of mature spirals billions of years later. Yet gravity's dominance faces a counterforce in the universe's expansion, which works not to gather matter together, but to carry everything apart. A tension between attraction and separation that defines cosmic evolution across all scales. Expanding space. Space itself grows larger with each passing moment, and expanding space does not move galaxies through some pre-existing void, but carries them along as the very fabric of distance increases, stretching the intervals between cosmic structures in a process that has continued for 13.8 billion years and shows no sign of stopping. The discovery of cosmic expansion ranks among the most profound shifts in human understanding. Before 1929, most scientists assumed the universe was static, eternal, and unchanging in size. Einstein himself found this assumption so compelling that he added a cosmological constant to his equations to prevent them from predicting expansion or contraction. Edwin Hubble's observations changed everything. Working at Mount Wilson Observatory with the 100-inch Hooker telescope, he measured distances to nearby galaxies using Cepheid variable stars as standard candles. Simultaneously, he examined their spectra and found that nearly all galaxies showed redshift. Their light was shifted toward longer wavelengths. More distant galaxies showed greater redshift. The relationship was linear. Redshift increased proportionally with distance. Hubble interpreted this as galaxies receding from us, with recessional velocity proportional to distance. His 1929 paper established what became known as Hubble's law, though the proportionality constant he derived was incorrect by a factor of about 7, due to errors in his distance measurements. The interpretation, however, was revolutionary. If galaxies are moving apart now, they must have been closer together in the past. Trace this backwards, and you arrive at a moment when all matter and energy occupied an infinitesimally small volume. Georges Lemaitre had already proposed this idea in 1927, calling it the primeval atom. We now call it the Big Bang. Crucially, expansion does not mean galaxies are moving through space away from some central point. Space itself is expanding, carrying galaxies along. There is no center to this expansion and no edge. Every observer, anywhere in the universe, sees distant galaxies receding proportionally to their distance, creating the illusion that they occupy a special location when in fact all locations are equivalent. The rate of expansion is described by the Hubble constant, currently measured at roughly 70 kilometers per second per megaparsec, though precise determinations vary depending on method, a discrepancy known as the Hubble tension. This means that for every megaparsec, about 3.26 million light-years of distance, the recession velocity increases by 70 kilometers per second. For the ancient galaxies observed by Webb, expansion has profound consequences. The light we receive left them when the universe was much smaller. During its journey, space has been continuously expanding, stretching the wavelengths of those photons. What began as ultraviolet or visible light arrives as infrared, shifted by factors of 10 or more. This cosmological redshift allows astronomers to calculate both distance and look-back time from spectral measurements. Expansion also affects our interpretation of these galaxies' properties. Their intrinsic brightness, size, and mass must all be calculated, accounting for the expansion that occurred while their light travelled toward us. Without these corrections, early galaxies would appear fainter and smaller than they actually were. Interestingly, expansion only affects distances between gravitationally unbound structures. Galaxies within clusters remain gravitationally bound and don't expand apart. The Milky Way and Andromeda are actually approaching each other and will eventually merge despite cosmic expansion. Gravity locally overcomes expansion's effects. The expansion rate itself has changed throughout cosmic history. In the universe's first moments, inflation drove exponential expansion. Afterward, expansion continued but decelerated as gravity worked to pull matter together. Then, roughly 5 billion years ago, expansion began accelerating again due to dark energy, an unexpected discovery that earned the 2011 Nobel Prize in Physics. Expanding space means the universe's history unfolds within a dynamic arena where distances themselves are fluid, where light carries embedded information about cosmic growth rates, and where the ancient galaxies we observe represent not just distant objects but moments captured from an era when space between structures was measured in fractions of what we experience today. Hidden physics. Every cosmological model rests on assumptions about how matter and energy behave under extreme conditions. Yet hidden physics, the phenomena and interactions that occur at energy scales, densities, or temperatures we cannot yet recreate or fully observe, may govern processes in the early universe that remain invisible to our current theoretical framework, operating just beyond the edge of what our equations can comfortably describe. Physics progresses by testing theories against observations, refining understanding when predictions fail to match reality. The ancient galaxies detected by Webb represent precisely such a failure, not catastrophic, but persistent enough to suggest that something in our understanding of early cosmic conditions may be incomplete. The standard model of particle physics describes 3 fundamental forces relevant at cosmic scales: electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity, described by general relativity, completes the picture. Together, these forces have successfully explained an enormous range of phenomena, from atomic nuclei to galaxy clusters, yet physicists have long suspected that this framework is incomplete. One possibility involves physics operating at extremely high energies or densities that existed during the universe's first moments but cannot be reproduced in terrestrial laboratories. The Large Hadron Collider, humanity's most powerful particle accelerator, reaches energies around 14 trillion electron volts. The early universe, during its first microseconds, operated at energies trillions of times higher. Whatever physics governed that epoch remains largely theoretical, inferred rather than directly tested. For early galaxy formation, hidden physics might manifest in several ways. Dark matter's properties remain mysterious beyond its gravitational effects. If dark matter possesses previously unknown interactions, perhaps coupling weakly to ordinary matter through forces we haven't detected, it could influence how efficiently the first galaxies assembled. Such interactions might cool dark matter halos more rapidly than standard models predict, allowing ordinary matter to collapse faster. There is also the matter of phase transitions. As the universe cooled, it underwent several critical transitions where fundamental forces separated from their unified high-energy state. The details of these transitions depend on physics at energy scales we cannot directly probe. If these transitions proceeded differently than standard models assume, they could have left the universe in a state more conducive to rapid structure formation. Quantum field theory suggests that vacuum itself possesses structure and energy. In the early universe, the vacuum state might have been different, with implications for how particles behaved and interacted. Some theories propose that the Higgs field responsible for giving particles mass could have had different properties at high energies, potentially affecting star formation efficiency. Another area of hidden physics involves the behavior of matter under the extreme densities present in protogalaxies. When gas collapses to form stars, quantum mechanical effects become important. The Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state, provides pressure that resists further collapse. But in the unique conditions of the early universe, higher background radiation, different chemical compositions, more intense gravitational fields, these quantum effects might have operated differently. Neutrinos, nearly massless particles that barely interact with matter, were far more numerous in the early universe. Standard models account for their gravitational effects on large-scale structure, but subtler influences might exist. Recent measurements have revealed that neutrinos possess tiny but non-zero masses, requiring physics beyond the standard model. These mass generation mechanisms might have additional consequences for early galaxy formation that current simulations overlook. The fundamental constants of nature quantities like the fine structure constant or the electron mass appear unchanging in the universe we can observe, but some theoretical frameworks allow these constants to vary with time or energy scale. If any fundamental parameters differed slightly during the first billion years, even by tiny amounts, the implications for star formation and galaxy assembly could be substantial. Hidden physics does not require exotic new forces or particles. Sometimes the challenge lies in calculating consequences of known physics, operating under extreme conditions that exceed computational capabilities. Beyond the complications of known physics pushed to extremes, there remains the possibility that entirely unknown forces shape cosmic evolution in ways we have only begun to glimpse. Unknown forces. Nature reveals its forces grudgingly, and unknown forces interactions that might exist beyond the four fundamental forces currently recognized could be operating throughout the cosmos, influencing galaxy formation and cosmic evolution in ways our instruments have not yet isolated, our theories have not yet anticipated, and our observations have not yet required us to acknowledge. The history of physics is a history of discovering forces. Electromagnetism emerged from separate observations of electricity and magnetism, unified by James Clerk Maxwell in the 1860s. The strong and weak nuclear forces were identified only in the 20th century through careful study of radioactive decay and atomic nuclei. Each discovery revealed phenomena that had always existed, but remained unrecognized until the right questions were asked and the right experiments performed. Current physics recognizes four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The standard model of particle physics describes the latter three with remarkable precision, predicting experimental results to extraordinary accuracy. General relativity describes gravity equally successfully across cosmic scales, yet both frameworks contain hints that they are incomplete. One persistent hint comes from the hierarchy problem. Why is gravity so much weaker than the other forces? At the quantum level, gravity is roughly 32 times weaker than the electromagnetic force. This enormous disparity seems unnatural, suggesting missing pieces in our understanding. Some theories propose additional dimensions of space where gravity propagates but other forces do not, diluting gravity's apparent strength in our three-dimensional experience. Extra dimensions could harbour additional forces that interact weakly or not at all with ordinary matter. These dark sector interactions might affect dark matter particles while leaving ordinary matter nearly untouched. If such forces exist, they could influence how dark matter clumps, potentially explaining why early galaxies formed more efficiently than expected. Dark matter might not be as cold or non-interacting as standard models assume, instead possessing a rich phenomenology in a sector we cannot directly access. Modified gravity theories represent another approach to unknown forces. Instead of adding new forces, these theories suggest that gravity itself behaves differently than general relativity predicts, particularly at large scales or in strong fields. Modified Newtonian dynamics, or MOND, proposes that gravitational acceleration follows different rules at extremely low accelerations, potentially eliminating the need for dark matter. While MOND struggles to explain many cosmological observations, more sophisticated theories like TeVS or emergent gravity continue developing, suggesting that gravity might be more complex than Einstein's equations indicate. Scalar fields, quantities that have a value at every point in space, could mediate entirely new forces. The Higgs field is one example, giving particles mass through their interaction with it. Other scalar fields might exist, influencing matter in subtle ways that become apparent only under specific conditions like those present in the early universe. Such fields might couple to mass or energy density, creating effective forces that strengthen in dense proto-galactic environments. Torsion, a geometric property of space-time distinct from curvature, appears in some extensions of general relativity. In Einstein-Cartan theory, torsion is generated by particle spin and provides a repulsive force at extremely high densities. This could affect how gas collapses in the early universe, potentially explaining rapid star formation without invoking new particles. The cosmological constant, or dark energy, remains one of physics' most profound mysteries. Its observed value is roughly 120 orders of magnitude smaller than quantum field theory, predicts a discrepancy so extreme it suggests fundamental misunderstanding. If dark energy is not truly constant but varies with time or responds to matter density, it would constitute a force affecting cosmic expansion in ways current models cannot capture. Quintessence and other dynamical dark energy models explore this possibility. String theory, which attempts to unify all forces, predicts additional forces arising from the vibrations of fundamental strings. The specific forces depend on how extra dimensions are compactified, curled up at scales too small to observe. Different compactification schemes yield different low-energy forces, only some of which might match our universe. Unknown forces need not be exotic to be important. Even within known physics, forces can combine in unexpected ways. In dense plasmas like those in the early universe, collective electromagnetic effects can create effective forces that resist or enhance collapse. Magnetic fields, amplified by early dynamos, might have provided additional pressure or channeled gas flows. The ancient galaxies observed by Webb do not definitively prove unknown forces exist, but they stress-test our physical understanding in regimes where gaps might lurk, reminding us that the forces shaping cosmic evolution may be more numerous and subtle than the four we currently catalogue. Theory limits. Scientific theories, no matter how successful or elegant, eventually encounter theory limits, boundaries beyond which their predictive power weakens, their assumptions become questionable, and their mathematics, though still technically valid, begin describing a reality they were never designed to address, revealing that even our best frameworks are approximations rather than ultimate truths. Isaac Newton's laws of motion dominated physics for 2 centuries, predicting planetary orbits with extraordinary precision, yet they contained limits. At velocities approaching light speed, Newton's equations failed, requiring Einstein's special relativity to correct them. In strong gravitational fields, Newtonian gravity proved insufficient, necessitating general relativity. Newton's theories weren't wrong. They remained perfectly adequate for launching spacecraft or designing bridges, but they encountered limits where nature behaves differently than Newtonian mathematics assumes. Cosmology faces similar boundaries. The lambda CDM model successfully describes cosmic structure across vast scales and epochs, predicting the cosmic microwave background's temperature fluctuations, the large-scale distribution of galaxies, and the universe's expansion history. Its success spans phenomena separated by factors of billions in scale and time. Yet this very success makes its limits more striking when they appear. One fundamental limit involves extrapolating backwards toward the Big Bang. Lambda CDM describes the universe from roughly 1 second after the Big Bang onward, with remarkable confidence. Before that moment, conditions become so extreme that quantum effects and gravitational effects become equally important, requiring a theory of quantum gravity we don't yet possess. General relativity and quantum mechanics, the 2 pillars of modern physics, become incompatible at such scales. The theory reaches a limit not because it's incorrect, but because it operates outside its domain of applicability. Another limit emerges at small scales in the early universe. Lambda CDM treats galaxy formation as a smooth, hierarchical process governed by gravitational collapse and star formation feedback. This works brilliantly for large structures and later epochs, but at the scales and times where the ancient galaxies observed by Webb formed, uncertainties multiply. How efficiently did the first stars form? How much did radiation from those stars affect surrounding gas? Did dark matter behave identically on galactic scales as it does on cosmic scales? Each question introduces parameters that must be estimated, rather than calculated from first principles. These aren't failures of the theory, but acknowledgements of complexity. Real galaxies contain billions of stars, vast quantities of gas experiencing turbulence, magnetic fields, chemical evolution, and countless other processes occurring simultaneously. Simulating all this requires computational approximations, subgrid models that represent unresolved physics through simplified equations. These approximations work well for modern galaxies where we can calibrate them against observations, but they become uncertain when applied to the early universe's different conditions. There is also the matter of initial conditions. Lambda CDM begins with the cosmic microwave background, describing how tiny density fluctuations grew into galaxies. But where did those fluctuations come from? Cosmic inflation provides one answer: suggesting quantum fluctuations during an exponential expansion phase created the seeds of structure. Inflation succeeds in many ways, yet it too has limits. Multiple versions exist, and the physics driving it remains speculative. The ancient galaxies challenge lambda CDM not by invalidating it, but by exposing where its predictions become less certain. The theory remains robust for describing the universe's overall evolution, but struggles with specific details of early galaxy formation. This is precisely what theory limits look like in practice. Not dramatic failure, but gradual loss of precision at the edges of applicability. Recognizing these limits doesn't diminish lambda CDM's achievements. Every theory has boundaries. The question becomes whether observations like Webb's require modest refinements within the existing framework, or signal something more fundamental, a limit that demands expanding the theory itself. Such questions lead naturally toward a deeper examination of how science processes uncertainty, and how cosmologists distinguish between problems requiring better measurements and those demanding new physics. Scientific doubt. Science advances not through certainty, but through scientific doubt, the deliberate, systematic questioning of even successful theories, a process that treats confidence not as a destination, but as a provisional state, subject to revision whenever new evidence suggests that what we thought we understood might be incomplete, inaccurate, or applicable only within narrower boundaries than we initially believed. This form of doubt differs fundamentally from everyday skepticism. Scientific doubt is constructive, methodical, and evidence-based. It doesn't reject theories capriciously, but tests them rigorously, seeking both confirmation and potential falsification. Karl Popper, the philosopher of science, argued that falsifiability, the capacity to be proven wrong, is what distinguishes scientific theories from non-scientific claims. Theories that can't be tested can't be doubted productively, and thus can't progress. The ancient galaxies observed by Webb exemplify how scientific doubt operates in practice. When first detected, these objects presented measurements that conflicted with predictions. They appeared too massive, too bright, too structured for their epoch. The scientific response wasn't to immediately abandon lambda CDM, but to doubt the measurements themselves, then the interpretations, then finally the underlying models in that order. Initial photometric redshift estimates, derived from analyzing light across multiple filters, placed some galaxies at extraordinarily high redshifts. Scientific doubt prompted spectroscopic follow-up, which measures precise wavelengths of specific spectral lines. Many initial redshifts required downward revision. Some galaxies thought to be at redshift 16 turned out to be at redshift 12 or 13, still remarkably distant, but less problematic for models. This doubt-driven verification prevented premature conclusions. Even confirmed high redshift galaxies required careful scrutiny. Could dust be affecting brightness measurements? Might gravitational lensing be magnifying their apparent size or luminosity? Are stellar mass estimates based on appropriate stellar population models for metal-poor early stars? Each question represents scientific doubt applied constructively, refining interpretations before declaring conflicts with theory. This process reveals doubt's essential role. It prevents both premature acceptance and premature rejection. The Hubble tension, the discrepancy between different measurements of cosmic expansion, illustrates this balance. Two independent methods yield expansion rates that differ by roughly 9%. For a decade, scientific doubt focused on potential systematic errors in either or both measurements. Each measurement has been checked, rechecked, and refined. The tension persists, now reaching a level where doubt shifts from questioning measurements toward questioning whether lambda CDM's simple assumption of constant expansion physics might need modification. Scientific doubt also recognizes the limits of human cognition. Confirmation bias, the tendency to notice evidence supporting existing beliefs, affects scientists as much as anyone. Peer review, independent replication, and adversarial collaboration serve as institutional implementations of doubt, ensuring multiple perspectives examine claims before acceptance. History demonstrates doubt's value. Continental drift was doubted for decades despite Wegener's evidence, because no mechanism was known. That doubt proved premature plate tectonics eventually provided the mechanism. Conversely, cold fusion claimed in 1989 faced immediate doubt because it conflicted with established nuclear physics. Despite some researchers' confidence, the claims couldn't be reliably replicated, and doubt prevailed. Knowing when to maintain doubt and when to update understanding separates productive skepticism from obstinance. For Webb's early galaxies, scientific doubt currently occupies a middle position. The observations are real, confirmed by multiple independent analyses. The tension with predictions is genuine but not catastrophic. Doubt focuses now on whether modest adjustments revise star formation efficiencies, refine dark matter behavior, improved computational models can reconcile observations with theory, or whether something more fundamental requires reconsideration. This state of productive uncertainty, where doubt drives investigation rather than paralysis, represents science functioning as designed, confident in methods, humble about conclusions, perpetually open to revision when evidence demands it, knowing that today's certainty might become tomorrow's approximation, requiring refinement or replacement by something deeper and more accurate. New questions. Every answer science provides births new questions, not as failures of understanding, but as invitations to look deeper, and the ancient galaxies revealed by Webb have generated precisely this kind of productive uncertainty, opening inquiries that weren't even formulable before we knew such objects existed, transforming what seemed like a complete picture of early cosmic evolution into something far more intricate and puzzle-worthy. The most immediate question concerns formation timescales. If galaxies assembled stellar masses of 100 billion suns within the first 500 million years, what process allowed such rapid accumulation? Standard hierarchical models suggest structure grows through mergers, small systems combining into larger ones over billions of years. Yet these early galaxies appear too massive for their age. If growth occurred only through mergers, did they form through a different mechanism entirely? Perhaps massive gas clouds collapsed directly into galaxies without first fragmenting into smaller protogalactic units, a process called monolithic collapse that would bypass the gradual hierarchical assembly. Another question involves star formation modes. The initial mass function, the distribution of stellar masses at birth, appears roughly universal in the present-day universe, with most stars being relatively small and only a few massive ones forming. But did this distribution hold in the early universe? If the first stars were predominantly massive, they would have lived briefly and exploded as supernovae, rapidly enriching their environments with heavy elements and allowing subsequent generations to form more efficiently. Webb's detection of carbon and oxygen in early galaxy spectra suggests this occurred, but the details remain unclear. How massive were these first stellar populations? How quickly did the IMF transition to its modern form? The role of supermassive black holes presents another mystery. Quasars, extraordinarily luminous objects powered by matter falling into supermassive black holes, have been detected at redshifts exceeding 7, meaning these black holes existed when the universe was less than 1 billion years old. Some possess masses exceeding 1 billion times that of the Sunday. Growing black holes this massive could. This quickly challenges theoretical understanding of black hole formation and accretion. Either they started from unusually massive seeds, perhaps direct collapse black holes forming from pristine gas clouds, or they accreted matter at rates exceeding theoretical limits. Webb observations might help distinguish these scenarios. There's also the matter of reionization's details. While the overall timeline hydrogen becoming ionized between 400 and 200 million years after the Big Bang is established, the specifics remain murky. Did reionization occur uniformly across the universe, or in patches that gradually merged? Which sources provided most of the ionizing radiation, small, numerous dwarf galaxies, or larger, rarer systems? How did the ionization state affect subsequent star formation? Early galaxies offer clues, as their spectra show absorption features created by neutral hydrogen along the line of sight, mapping reionization's progress. Dark matter's behavior on small scales generates additional questions. Lambda CDM predicts dark matter should form numerous small halos in the early universe, each potentially hosting a dwarf galaxy. Yet observed early galaxies appear relatively massive and bright. Either the small halos exist but fail to form visible stars, or dark matter behaves differently than standard models assume, perhaps possessing weak self-interactions that suppress small-scale structure. Chemical evolution puzzles also emerge. The heavy elements detected in early galaxies require prior stellar generations, but how many cycles of star formation and death occurred before these galaxies became observable? Can we detect even earlier systems representing the first stellar populations? Or did those initial stars form in objects too small and distant for even Webb to resolve? Each question connects to others, forming a web of uncertainty that maps the boundary between knowledge and ignorance. These aren't questions born from failure, but from success, from observations detailed enough to reveal complexity where simplicity was assumed. The ancient galaxies have shown us what exists at cosmic dawn, and in doing so, they've revealed how much remains unknown about how those structures came to be, how quickly they evolved, and what physical processes governed their assembly during the universe's most formative moments. Answering these questions requires not just better theories but better observations, instruments capable of seeing further and clearer into cosmic history than ever before. Future eyes. Astronomy advances through better instruments, and future eyes telescopes planned or proposed for the coming decades will extend our vision deeper into cosmic time, resolving fainter structures, capturing more detailed spectra, and potentially witnessing the universe's very first luminous objects, pushing observational boundaries toward the limits of what physics allows us to see. The James Webb Space Telescope, launched in 2021, represents humanity's most powerful infrared observatory, but it's not alone. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will complement Webb with a field of view 100 times larger while maintaining comparable sensitivity. Roman's wide-area surveys will catalogue thousands of high redshift galaxies, providing statistical understanding of early galaxy populations that Webb's deep but narrow observations cannot achieve alone. Where Webb offers detailed portraits of individual ancient galaxies, Roman will deliver a census revealing how common such objects are and how their properties vary. Ground-based observatories continue advancing as well. The extremely large telescope in Chile, with a 3.9-meter primary mirror, will begin operations in the late 2020s. Despite atmospheric interference, its enormous collecting area and adaptive optics systems, which correct for atmospheric distortion in real time, will enable spectroscopy of faint early galaxies, measuring their chemical compositions, kinematics, and internal structure with precision impossible from space-based telescopes' smaller mirrors. The giant Magellan Telescope and 30-meter telescope, both under construction, will provide complementary capabilities. These facilities will study individual stars in nearby galaxies, offering insights into stellar populations that inform our understanding of star formation in the early universe. They'll also observe gravitational lensing events where foreground galaxy clusters magnify distant background galaxies, effectively creating natural telescopes that amplify faint early systems. Radio astronomy offers another window into cosmic dawn. The Square Kilometre Array, an international project distributing thousands of antennas across Australia and South Africa, will detect the 2.1 centimetre line of neutral hydrogen redshifted from the epoch before reionization. This radiation doesn't come from galaxies but from the intergalactic medium itself, mapping how reionization progressed spatially and revealing regions where the first stars and galaxies formed. Looking further ahead, more ambitious concepts emerge. The Habitable Exoplanet Observatory, currently in early planning, would primarily search for biosignatures on Earth-like planets, but could also conduct deep cosmological surveys. A proposed successor to Webb, sometimes called the Origins Space Telescope, would operate at longer infrared wavelengths, detecting even cooler dust and probing galaxy formation at the earliest possible times. Perhaps most ambitiously, proposals exist for space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna. While primarily designed to detect gravitational waves from merging supermassive black holes, LISA could observe black hole mergers from cosmic dawn, revealing how these enigmatic objects formed and grew during the universe's first billion years. Each instrument addresses specific questions while generating new ones. Roman will reveal how common massive early galaxies are, determining whether Webb's discoveries represent rare exceptions or typical examples. The ELT will measure detailed chemical abundances in early systems, tracking how quickly the universe became enriched with heavy elements. The SKA will map reionization directly, showing where and when the first sources of light emerged. Theoretical advances will accompany instrumental ones. Computational simulations grow more sophisticated as computing power increases, incorporating physics at smaller scales and modeling feedback processes more realistically. Machine learning techniques help analyze vast data sets, identifying patterns and anomalies that human inspection might miss. The synergy between these capabilities matters most. Webb identifies intriguing targets. Ground-based telescopes follow up with detailed spectroscopy. Roman provides context by surveying surrounding regions. Radio arrays map the neutral hydrogen environment. Each piece contributes to a comprehensive picture that no single instrument could provide. Future eyes will not merely see further, but see differently, combining wavelengths from radio waves to X-rays, temporal scales from milliseconds to years, and spatial resolutions from individual stars to cosmic structure spanning billions of light years. They represent humanity's expanding capacity to witness the universe's story, observing light that has traveled across almost the entire age of the cosmos to reach us. The ancient galaxies that currently puzzle cosmologists will become, in time, thoroughly understood examples preparation for the next generation of mysteries that better instruments will inevitably reveal. Silent universe. Space transmits no sound, and the silent universe unfolds its grandest dramas, stellar explosions, galactic collisions, the birth of worlds in absolute quiet, a reminder that the cosmos operates at scales and in conditions fundamentally alien to human experience, where even the most violent events occur in a vacuum that prevents vibration from becoming the pressure waves we would recognize as noise. This silence is not metaphorical. Sound requires a medium air, water, solid matter through which pressure waves can propagate. Molecules must collide, transferring energy from one to the next, creating the compressions and rarefactions that our ears detect as sound. In the near-perfect vacuum of space, where matter is so sparse that cubic meters contain only a handful of atoms, there is simply nothing to carry these waves. A supernova exploding with the energy of 1 billion suns produces no sound. A galaxy rotating over millions of years generates no hum. The universe's most spectacular phenomena occur in silence. This creates a peculiar disconnect between cosmic violence and human perception. When we visualize the early universe in intense radiation, colliding clouds of gas, the first stars igniting, we naturally imagine noise accompanying such drama. Yet the reality is quieter than the quietest room humans can construct. The anechoic chambers used to test sensitive equipment achieve noise levels around -20 decibels, but even these contain air molecules creating faint thermal noise. Space offers silence far more complete. The cosmic microwave background, that ancient radiation filling all of space, provides a curious exception of sorts. While the CMB produces no sound in the conventional sense, astronomers have converted its temperature fluctuations into sound waves, mapping variations across the sky to audio frequencies. The result is a deep hum with overtones, something like the lowest note on an organ combined with higher harmonics. This sound of the Big Bang represents what the early universe's density fluctuations would have sounded like if converted to pressure waves in Earth's atmosphere. A creative interpretation rather than actual, cosmic noise, but one that makes the abstract notion of primordial fluctuations more tangible. Within galaxies, conditions change slightly. The interstellar medium, while still an excellent vacuum by terrestrial standards, contains enough matter for extremely low-frequency sound waves to propagate. These aren't sounds human ears could detect. Their wavelengths span light-years, with frequencies measured in nanohertz, but they represent actual pressure waves travelling through the thin gas between stars. Supernova shock waves compress this medium, creating sound waves that propagate for thousands of years before dissipating. The Crab Nebula, remnant of a supernova observed in 1054 AD, still rings with these ultra-low frequency vibrations. Black holes add another dimension to cosmic silence. When two black holes merge, they emit no light, no particles, only gravitational waves ripples in space-time itself. These waves compress and stretch space as they pass, but they don't interact with matter the way sound does. The LIGO and Virgo detectors, which discovered gravitational waves, convert their signals to audio frequencies for analysis, creating the famous chirp of merging black holes. But this chirp is an artifact of data processing, not actual sound. The merger itself occurs in silence, space warping and reforming without producing a single vibration in any material medium. The ancient galaxies observed by Webb formed and evolved in this soundless environment. Their stars ignited silently. Their gas clouds collapsed without thunder, Supernovae exploded, black holes accreted matter, and entire stellar populations lived and died without making the slightest noise. The universe's most formative epoch unfolded in absolute quiet, governed by gravity and radiation pressure and nuclear fusion, none of which require or produce sound. There's something oddly appropriate about this silence. Sound is a phenomenon of relatively dense matter, atmospheres, oceans, solid substances. It belongs to the realm of planets, to environments where matter is compressed by gravity into states where molecules touch and interact constantly. The cosmos at large operates in a more austere regime, where matter is so diffuse that neighbouring atoms might be separated by meters or kilometres, where energy manifests as light and gravitational fields rather than mechanical vibrations. This silence also means that most of cosmic history has occurred without witnesses capable of hearing it. Life, as far as we know, exists only on planets with atmospheres precisely the environments where sound can exist. Before Earth formed, before any planet developed conditions suitable for life, the universe had already existed for over 9 billion years, conducting its business in silence, assembling galaxies and forging elements and organising structure across billions of light years, all without any possible listener. Yet in that silence, light travelled unimpeded, carrying information across cosmic distances without degradation, allowing creatures that eventually evolved on one small planet to look backward through time and reconstruct events that occurred before that planet existed. The silent universe preserves its history in light rather than sound, in electromagnetic radiation that crosses vast distances unchanged. Each photon, carrying news of the moment, it was emitted a message written not in pressure waves that would fade after propagating through a few kilometres of air, but in wavelengths and frequencies that can endure for billions of years. And within that enduring record lies a mystery that sound could never convey, the puzzle of how everything came to be. Endless mystery. The universe does not offer final answers. An endless mystery defines not the limits of human knowledge but the nature of reality itself, where each solved puzzle reveals deeper questions, each observation opens new uncertainties, and the ancient galaxies that challenged our cosmological models represent not an endpoint but another chapter in an investigation that extends backward to the beginning of time and forward indefinitely into whatever future humanity possesses. This is not a defect but a feature of the cosmos. Reality appears structured in layers, each level revealing new complexity when examined closely enough. Atoms were once thought indivisible. The word itself means uncuttable in Greek, until experiments revealed protons, neutrons, and electrons. These in turn proved composite, made of quarks and leptons. Whether quarks represent the final layer or themselves possess structure remains unknown. Each answer generates the next question. Cosmology follows the same pattern. When Hubble discovered cosmic expansion, it raised immediate questions about what preceded it. The Big Bang Theory answered some of these but created others. Why did the universe begin? What determined its initial conditions? Cosmic inflation provided partial answers while introducing new puzzles about what drove inflation and what existed before it began. The ancient galaxies continue this tradition. Webb's observations resolved one question: do massive galaxies exist at high redshift? Affirmatively, but in doing so generated dozens more about formation mechanisms, dark matter behaviour, reionization, and star formation efficiency. This is progress, moving from vague uncertainty towards specific, answerable questions that can guide future observations and theoretical work. Philosophers of science have noted this pattern. Karl Popper emphasized that science grows through conjecture and refutation, each disproven theory bringing us closer to truth. Thomas Kuhn described paradigm shifts where anomalies accumulate until a new framework emerges. Both perspectives recognize that scientific understanding evolves rather than concludes, approaching but never quite reaching complete explanation. The endless nature of cosmic mystery stems partly from practical limits. The universe's finite age creates a horizon beyond which light has not had time to reach us. We cannot observe what happened before the cosmic microwave background was released, because light could not travel freely before then. This represents a fundamental boundary, not a temporary obstacle awaiting better instruments, but a permanent limit imposed by physics itself. Yet even within observable boundaries, mysteries persist. Dark matter comprises 27% of the universe's energy content, yet its particle nature remains unknown despite decades of detection experiments. Dark energy, making up 68%, is even more mysterious we observe its effects on cosmic expansion, but possess no accepted explanation for its existence or magnitude. Together, these dark components constitute 95% of the universe. We've identified what they do without understanding what they are. The ancient galaxies contribute to this ignorance in productive ways. Their existence suggests our understanding of the remaining 5% ordinary matter also requires refinement. If galaxies formed faster than predicted, perhaps star formation physics in the early universe operated differently. If dark matter halos collapsed earlier than expected, perhaps cold dark matter assumptions need adjustment. Each possibility opens research directions that will occupy astronomers for decades. There's a peculiar comfort in this endless questioning. If the universe offered simple, complete answers, if every observation confirmed predictions perfectly, the enterprise of science would terminate. Mystery drives investigation. The questions Webb has raised about early galaxies will motivate the next generation of telescopes, which will answer some questions while inevitably raising others, continuing a cycle that has characterized astronomy since ancient humans first wondered about points of light in the night sky. Human history demonstrates this pattern's persistence. For millennia, cosmic mysteries were attributed to gods or considered permanently unknowable. The scientific revolution revealed that systematic observation and mathematical reasoning could answer questions about planetary motion, stellar distances, and galactic structure. Yet this success didn't eliminate mystery, it refined our questions, transforming vague wonder into specific inquiries amenable to investigation. The ancient galaxies represent the frontier of this process. A century ago, astronomers didn't know galaxies existed outside the Milky Way. 50 years ago, the Big Bang theory was still contested. 20 years ago, dark energy was newly discovered. Today, we observe galaxies forming within the first billion years of cosmic history and find that our models, sophisticated though they are, require adjustment. Tomorrow's astronomers will look back on our puzzlement with understanding, having answered questions we're only beginning to formulate, while facing mysteries we cannot yet imagine. This progression suggests that mystery is not a temporary condition awaiting elimination, but an intrinsic property of a universe complex enough to generate conscious observers. Every layer of reality we peel back reveals another beneath it. Every question we answer spawns new ones. The cosmos appears inexhaustible in its capacity to surprise, challenge, and invite further investigation. The ancient galaxies, breaking cosmological models with their unexpected mass and structure, exemplify this dynamic. They are not failures of science, but invitations, challenges issued by the universe itself, reminding us that reality exceeds our theories, that observations trump predictions, and that the cosmos will forever remain slightly beyond our complete comprehension, offering endless opportunities for discovery to any species patient and curious enough to continue asking why.